Hi, my name is Eric Carlson. I'm with the Michigan DOT. I'll be your moderator for this session, Drainage and Erosion Control. Our first speaker is Dr. Marta Sitek. Did I say that right? Okay. Marta graduated and later worked as an assistant professor at the Faculty of Civil Engineering, Warsaw, Warszawa University of Technology in Warszawa, Poland. She currently works as a principal mechanical engineer at Argonne National Laboratory in Lamont, Illinois. Her expertise is in computational structural mechanics and computational fluid mechanics modeling and analysis. She contributes to the work for the hydraulic research program at FHWA's Turner Fairbank Highway Research Center, and she performs research, analysis, and computation for the projects managed and coordinated by state DOTs. Please welcome Marta.
Hello, everybody. I've probably talked to most of you, but if I haven't yet, sorry about that, didn't have enough time to do it. This presentation is about the work that we've done with Dr. Stephen Lottes, who couldn't be here today and present it with me. And absolutely nothing would also happen without Colonel Karenig, who's been managing the Transportation Pooled Fund, where the funding came from. If you want to learn anything about the Pooled Fund, about the projects that we've been working on, the work that have been done, you please go to the pooledfund.org. You will see there that we upload quarterly reports about our work. These are pretty short documents, but they summarize the progress. If you are interested in anything in more detail, if you go to osti.gov and type in my last name or Steve's last name, you will see a lot of reports that we've written up so far. So one of the main projects that we've been working on is the water accumulation on pavements. And it can be, we've been looking at on different aspects. So we've been looking at the accumulation of water film thickness, for example, on the transition to superelevation. We've been looking at the infiltration through pavements or soils. And even in this one topic, we've been looking at different levels of complexity of the model, of the, let's call it a soil sample. So, but what I would like to talk about today is the roadway drainage and inlet analysis. So, again, huge thanks also to South Carolina DOT and Ohio DOT for believing in us and letting us have fun a little bit with the catch basins. And so for South Carolina DOT, we've done the Great Inlet CB25 and curb openings, CB16 and 17, as well as combination inlet CB1. A report on CB25 has been already published. The other one is in internal review. For Ohio DOT, the first phase was on combination inlets, CB3, CB3A, in on-grade and sump in SAG locations. And the ongoing research covers Great Inlet CB6 and inlet number 3 for single slope barrier. We've been also looking at something that probably everybody has seen at some point in HEC 22. So I took some of the standard drawings from HEC 22, recreated the geometry of 3 grades that I will be talking about later on, which is the 45 tilt bar grade, P50 grade, and curved vein grade. And we were also looking at their performance. And because we're never in a void, we like to compare our results with existing data. So for example, for the sump conditions, we were looking at the HEC 22 chart 9A and B, and comparing our results with those presented there. So whenever we are modeling something in CFD, in computational fluid dynamics, we always have to take a lot of different parameters into account. We have to be very careful with the geometry because that could change our result. We have to look at the size of the domain, how to discretize it, what should be the time step, time discretization, what should be the boundary conditions and whatnot. So I could be talking about it, well, for a few hours probably, if you only let me. But today I wanted to talk about one more thing that's very important, which is modeling of the pavement roughness. Because as you all know, the velocity of the flow, the spread of the flow, it depends on the roughness. But in Manning's formula, we have this beautiful coefficient, Manning's coefficient n, which we cannot use directly in CFD. We have to translate it into something that would be understood by the software, which is, or could be, roughness height. And for that also we have a few different models available. We've been using the Colebrook-White formula. We found it to be probably the most accurate, at least out of those that we've tested. And the way in a model that I can represent the roughness of a pavement is either through so-called wall functions, which is basically just a relationship between the velocity and distance from the pavement. So the profile changes due to roughness. And we've been, for the last year or so, we've been looking into quite a detail into this. The other thing that we've proposed was to use a porous media model for the roughness. So the Ks, the roughness height, thickness of a porous region, and then so porous region, so with flow resistance, which would be greater than 0, and above it would be a fluid region with no flow resistance. So the third level of complexity would be a meshed out geometry of the surface. So it could be either a scan of a sample or kind of made up by me, usually a surface of, created from small grains of different sizes. We've been working on that as well. So depending, of course, on the application, the complexity level will or may change. In this case, we've been using, because we've been modeling most of the time the full scale cases, so we have a 2-3 wide lane roads with a proper distance from the inlet to the domain to the drain, and then from the drain to the outlet. So we've been using the first two approaches so far. The third one takes a lot of computational resources and time. So for the on-grid locations, we always look like I just mentioned. We are taking a section of a road which could be just represented, the cross-section could be represented like this. We have a inlet flow. The flow is going to the right, and it can either end up in the grate, in the curb opening, or whatever other drainage. So it will be intercepted by the inlet, or it will bypass it and will go through the other surface. What we're modeling is we are solving 3D CFD equations with so-called VOF model, which is a volume fraction of fluid model. So this model allows us to calculate the surface, where the surface or surface of the water or interface between water domain and air domain is. And that's the result that one of the results that you're seeing here. During a simulation, we can monitor how the intercepted flow changes and how the bypass flow changes. Also, we're looking at, because that's what we were asked for, the front flow into the grate or other inlet, side flow, and back flow. So we can, during a simulation, depending on what kind of monitors I set up at the very beginning of the simulation, we can look at all of those interesting to you parameters. And the main results that we are always asked to provide are the efficiency curves. So just two examples. On the left side, efficiency curves for CB16. On the right side, efficiency curves for CB3A with varying longitudinal slope and upstream flow rate. So thanks to this, you can see that, for example, the CB16, we were able to model from 0.3% of longitudinal slope up to 16%, because that was the requirement. For the CB3A, we were looking at the range from 0.25 to 8%, and also slightly different flow rates. The other thing that we always do, like I mentioned, we always compare with existing results. So for example, on the left side, you can see a comparison of efficiency from CFD versus efficiency calculated with the equations that we found in HEC 22. On the right side, we were comparing our computational efficiencies with the ODOT design equations. And also, as you can see, and I know that another presentation will be on curve openings, we do see some discrepancies between the efficiency that's calculated by or with equations from HEC 22 as compared to the computational results. But when it comes to the combination grade, which is CB3A, the results are well within the plus minus 20% of difference between the two. We're also looking at SAG locations. So here we have a slightly different situation. We have like our computational domain is like a tank filled with water, and we're draining this water only through the catch basin. And we can record the flow rate through the inlet and the water depth at the curb. And so then we can create plots like this, or what some people prefer in a log scale, because then you can, for example, compare with that chart 9A that I mentioned before. And the really fun part was that last year we were able to, well, not me, but Cornell and his team, they were able to perform some physical tests for us so that we can use them for validation of our models. And so they prepared part of the flume, prepared the entire setup. They 3D printed the grades that you can see on the bottom left of the slide. All I had to do was to replicate it in CFD. So basically, I just took all of the dimensions. I didn't put in the flow straighteners just because we decided that they will not change the results much. And we were able to compare our results. So on the left side, you can see three different views of the grade, P50 grade in this case. I'm just showing a few example results because otherwise, again, it would take too much time. And on the right side, my simulation results. And they look, just looking wise, they look pretty good. They look pretty comparable. And when you look at, again, the plot of water depth versus flow rate, you can see that the comparison is really satisfying, I would say. To me, at least. So what you can see here is that we have two types of experiments, two types of CFD. So we had steady state and transient. And just because we just finished this, I don't have much more to say about that. Hopefully, we can show it at TRB in January and talk more about it then. Somebody tell me if I'm running out of time. Maybe not yet. So what we've also been asked to look at is the inlet clogging. And yes, and I had a lot of fun with this one. We could model it this way. So prepare some made-up sticks and leaves and run them through a computational domain. But much easier and much more effectively, you can model clogging of a grate or a curb opening by just closing off parts of the grate or said curb opening. In this particular case, that was the Ohio grate, one of the Ohio grates, we've noticed that even though the grate interception, of course, decreases, but the curb is kind of taking over, and the overall decrease in the efficiency of this combination inlet does not drop much, just from 62% to 59%, depending on the clogged fraction of the grate. The other fun thing that we worked on was for South Carolina DOT, and they asked us for the CB25 and then CB16, 17, and CB1 for spreadsheets that could be used to design inlet spacing. So like just a useful tool for them in their daily work. So in this case, you can put in the green, okay, so the green columns are where you need to put in some values, some variables that you want. So for example, runoff coefficient, road weight width, shoulder width, longitudinal slope, and everything else, all of the other, the white cells would be populated with the results of calculations, which are based on our CFD results for this particular inlet. And because I was talking quite fast, I made it in 21 minutes. Or not even that, 15, wow. So thank you for your attention. And if you have any questions.
Any questions for Marta?
Yes.
Marta, have you looked at inlets in series? Oftentimes, we'll put them in series. Did you look at like blended inlets?
Actually, we did. Again, just for fun, nobody asked us to do it. But in the report for South Carolina CB25, we put in one chapter where we did this kind of a study. So it also can be done, and like an optimum distance between the two can be established from these computations as well.
Can I pick a second one?
Oh.
What is it?
We have 10 minutes, I think, right? All the questions in the world.
Sometimes we're coming down off a bridge, and somebody always puts an intersection at the bottom of the hill, and you've got to catch the water, and you end up putting inlets across the shoulder. It's kind of unorthodox. Does that operate as a big inlet? How do you I'm sure that messes with the flow somehow. Where you have them like going across the road.
Oh, they go across? Across the, we did not look at this. Yeah.
Just gave her something fun to do.
That would be interesting to see.
Desperation is what it is.
Okay, question from Marta.
Yes.
How do your results compared with the manufacturer's
We didn't get really the results from the manufacturers.
We did not look at that.
Okay.
We just looked at what you gave us. Our interest really was redesign, slightly different from what X1 says.
Really?
We were interested in how effective it is.
Sure. So it looks like we're doing it right.
Yeah, we're doing it right.
And I have one more answer to this. The only thing that we actually, and that's why the physical testing of the sound conditions was that when you, Jeffy, gave me the standard drawings from the manufacturer, and it said that for some conditions use a much smaller opening area. I'm like, oh, why? It seems like that's slightly over-conservative. So we were wondering what was the cause of it, are my computations wrong, or maybe there is something else behind it. So that's why we did the validation for this case. Yes. And so yes, please, TRB, next TRB, January, hopefully.
Got another question back here.
So common practice in South Carolina is using geopath drainage. Do you compare with that software package to see?
But which software package?
Bentley's geopath drainage.
No, I've never had a chance to.
And we are moving also to Stonecat or Silverstone. So I don't know if those packages
I never looked at it. I don't even know how they work, what they are based on. But I will definitely do.
Exactly, because it's important to link common practice in the consultant digital world.
Oh, absolutely. So in this case, I think that the link is that right now, for example, Ohio DOT, they know that their design equations give very similar results to our computations. So basically, I think that, I don't know if you maybe want to talk about the conclusions, if there are any.
I mean, that's really what we're looking for. I mean, we don't use the Hex 22, which uses velocity splasher, but we don't use that. So we use a slightly different method. Our methods, which Marta was able to help us figure out where they came from, they're from just old hydraulic engineering.
Oh yeah, that was like a detective's work.
That's really where it came from, because our code was written in segments for you, and we just keep bringing it forward. So it kind of makes sense.
Yeah, and there were some handwritten notes, and we were trying to figure out why and what's going on. But on the other side, for South Carolina DOT, they asked us to prepare the spreadsheet. So that's what we did, and Excel spreadsheet. I would say that everybody can use it.
Yeah,
Yes, I should have asked you as well.
So we use those for this information between the catch basins. But then we use the geopath calculations of pipes system. So once we get that information,
So it's
independent.
yeah, good.
So I couldn't hear, maybe some of the discussion was already talked about a little bit, but it seemed like you were kind of comparing CFD results to the design guideline in one of the inputs.
Correct.
And I think the first one was showing a pretty significant difference.
Yes, for the curb opening.
Right. And did you do a deep dive on what in the original design guide, what was leading to that? Or was it faulty data or something like that?
You are very lucky because these two will talk about it later.
Oh, yeah.
That's exactly the topic. Am I right? Am I right?
Is it the 100% capture?
Well, curb openings and the efficiency, yes. So basically, we've noticed, and I think that your conclusion was the same, that Hex 22 is slightly over-conservative for certain cases. I just wanted to be nice.
So you modeled the clogging
Correct.
on the inlet. How did that affect the flow, not just the capture,
Bigger spread.
but the parameter, the way the flow occurred around the inlet?
Well, of course, it was different. If you want like snapshot of the steady state, I would refer to our report. It did change slightly, yes. The flow was spreading more around it. It would go outside also, go slightly back into the into the inlet, or it would bypass.
Got 5 more minutes if there's any other questions.
What did I do to myself?
Marta, we're all jealous, and I'll tell you why we're jealous. Because all the road designers in here want to be able to run computational fluid dynamics on their actual designs. And where I'm dovetailing my question is, can you talk about the computational power and resources that it takes to do your CFD? And
Yes.
obviously that might not be scalable for us to do it on the
I would start with the fact that and Hubert is here. Yes, so he is my manager and he knows everything about computers and computational power. That's why, and also how much Starsteam Plus costs, which I do not remember right now.
We pay in the neighborhood of 100,000 right now per year, the licensing fees for the CFP software itself.
So that's one hurdle.
That's one cost.
The other, yes, the other one is the maintenance of the cluster. And third is that, well, it depends when it comes to the computational time or computer time. It can go from a few hours to a few days. All depends on the complexity rather of the model.
So we're not there.
No? I don't
Not
think so.
quite.
Not quite?
Not quite.
Yes, that's a good answer.
I think that's a good
Thank you for helping me out.
So the newest hardware you can buy these days, like 64, 128 core EPIC processor systems, get pretty much the computing power to do something like this on your own, right? You're racking up. And software is another thing, and that's one of the reasons why we're developing all the other things like Discover software, also in our phone, because that software is available for free, right? And eventually, you know, runs of these things, so there's no problem. But it provides potentially a tool for the future to hand over to somebody and say, here, with that framework, you can do it fairly easily, right? I would say there's still years away from that, maybe 4. I mean, I don't know any promises, but we have a very clear indication that individual computers that you can manage as a Windows computer will be able to do that eventually.
All right, let's do one more question.
Taking up this gentleman's question, although we might not invest in a supercomputer, one could call your facility directly and say, we would like so much time.
One could call Cornell. Very good question. Thank you for this question. Or one could go first to one of those websites, read about what we've done, and if they think that it's worth it.
All right, everybody, let's give her a hand.